You would think that after going through so many of these videos, we would just get to be to a point where this is old hat. But every single time we push that record button, it's like brand new every single time. So I hope you give your teachers a little bit of credit. This is G today, and I'm going to be helping you through all three sections of 2.6, which is going to be about rational functions over the next couple of days. So bear with me, pause, go back, take a look at stuff. If I make a mistake, I'll probably make amendments to this. So we'll see what we end up coming up with. Now, taking a look at a couple of review questions that are at the beginning of this. I'm talking about how many possible real zeros or positive real zeros we might be looking at here. Remember that if we're just trying to look at the number of possible positive real numbers, we're probably looking at Descartes' rule of signs. And that rule of signs really only cares about whether or not there's any sign changes between them and then a multiple of 2 less than that. Excuse me. Sorry about that. Sneezed. No, I don't have COVID, so I think we're all right. Now we're going to take a look at the number of sign changes that we're seeing here. So between each one of these in descending order, we've got 1 sign change, 2 sign changes, 3 sign changes, which would mean, since we're doing the positive one, that we would have an expectation of either 3 positive answers that are real zeros or 1, because it's always 2 less than the amount that we come up with in terms of the number of sign changes. So if we had 4 sign changes, we'd be looking at 4, 2, or 0. If we had 1 sign change, it'd be only 1 sign change, and so forth. So I hope you have that rule of Descartes' rule of signs in the back of your mind. It can really be helpful. It's a relatively easy technique to check to just see which of your P over Q roots are really the worthwhile ones to try. What would be the possible rational zeros that you would want to try from up there? That would ultimately be taking a look at the constant term at the end, P, and the linear or the term in front of the lead term coefficient, which is Q, and we would do a P over Q possibility list. And in this case, P happens to be plus or minus 1, 3, or 9, and the bottom would be 1 and 3. Now, if we look at all the possible combinations of that, we would definitely have plus or minus 1, 3, and 9 by dividing by 1. Then when we divided by the 3, we would get extra ones of 1/3. The 3 divided by 3 would be 1 again, and the 9 divided by 3 would be 3 again. So ultimately, the possible zeros we'd be looking at would be 1, 3, 9, and 1/3, plus or minus those. End behavior for a 2 over x. Now, this is going to be something that we're going to be focused on for the next couple of sections, is looking at what these graphs look like. The general possibility that this 2 over x would generate would be a rational function that would look like this, and ultimately its end behavior would be headed towards, if it's going towards negative infinity, it'd be heading towards 0. And if it was headed towards positive infinity, it'd be headed towards 0 as well. Now, normally when we talk about end behavior, we're very focused on the x or domain possibilities of this. And the reason why this one is going towards that, because the horizontal asymptote is at 0. Now, we'll talk more about this. This kind of leads me down here to our goals today, and that's to help us define where the vertical and horizontal asymptotes of rational functions would be. Now, let's kind of go through each one of these steps. And in some of these, I agree and disagree that they're worded in certain ways. So it says all x values that will produce a y or f of x value. So the domain, when we start talking about it, is if you plug something in, is it going to give you something out? That would be a valid domain. Okay, and we're not talking about domains that end up generating asymptotes or horizontal asymptotes. We're ultimately saying, is there an x value that can be determined and make a y? Now, when you run into vertical asymptote situations, this is an x that the function is undefined at. It's a place where the function can't quite reach to, as long as it's not a hole. Now, the graph can not cross the vertical asymptote. The vertical asymptote acts like a wall. And ultimately, the graph will get closer and closer to that until it exceeds past that domain, and then it occurs on the other side of it. But it never, ever quite reaches it or technically crosses it. Now, on the other hand, a horizontal asymptote, or an HA, is a place where the graph actually levels off. And the leveling off horizontally, now it is not as rigid as the vertical asymptote. It is more of a semi-permeable membrane, to go from biology, and it ultimately can be crossed in certain circumstances. It doesn't happen often, but it can. Although the VA can't be crossed, graph sometimes can cross an HA, as I said before. Although there can be several VAs on a graph, there will be at most only one horizontal asymptote. You only get one of those. Now, some general rules on how do you actually find some of these. In order to find a vertical asymptote, that's going to be the biggest thing here, you're going to take the denominator and you're going to set it equal to 0. So it is from the bottom. I always kind of think of, instead of denominator, I go VAs are from the bottom. You want to look to the bottom to figure out where they're at. If there's a repeating factor, and this statement right here is the one that I have the hardest time with, if there's a repeating factor in the rational function, then there's a hole in the graph. It actually turns out if there's a repeating factor between the numerator and the denominator, if there's a factor that's, say, up here and it's a factor down here that actually has something in common, that cancellation will generate a hole in regards. So pay attention to that. I don't think it's just necessarily that it's a repeated factor. You can have repeated factors in a denominator and it only ends up generating one vertical asymptote. Now, in order to find a horizontal asymptote, it's not as easy as looking for a vertical. Vertical, you just go to the bottom, you set it equal to 0, and you solve for it. A horizontal asymptote has a set of rules that are associated with it. And these N's and M's are all about the degree of the numerator and the degree of the denominator. It's about the power of the two individual parts of the rational expression that make the determination of it. So now this one says that the numerator has a lesser power than the denominator does. For example, we could have something like 3x on the top and 5x squared on the bottom. Definitely the power in the top is losing the battle to the bottom. If this turns out to be the case, the horizontal asymptote is, the HA in this case, is y equals 0. It turns out that the x-axis is the horizontal asymptote. This is where we would draw the horizontal asymptote right here on the x-axis. That's because the top is losing the battle based on degree to the bottom. Now, if it turns out that the two degrees turn out to match one another, let's say, for instance, I was dealing with x plus 5, and this one was, say, x minus 6, the degrees on these polynomials is the number 1. We've got a degree of 1 and a degree of 1, so they match each other out. If that turns out to be the case, then the horizontal asymptote is thoroughly convinced that it is a y is equal to a over b. Now you're probably thinking, what the heck is y over b? It's these lead term coefficients in the front of these leading terms that are holding the power on is what determines the horizontal asymptote. So in this case it'd be 1 over 1, or the horizontal asymptote would be 1. So pay attention to the fact that the degrees end up matching each other, and you can determine the horizontal asymptote in that case. Now, you've got all these different possibilities. You've got that it's x, y is 0, or y is equal to a over b. Well, if it turns out that the top wins the battle over the bottom, I'm going to make this very distinct, that it's like x squared plus 5x plus 6, something like that. Definitely a third power polynomial is winning the battle over the top of the bottom's degree. The horizontal asymptote in this particular case does not exist. And you end up with some very unorthodox graphs that fall into this particular category where they have no horizontal asymptote whatsoever. There isn't some number that they both approach. Okay? Now, let's put this to a little bit of technique to try and figure it out. So the questions that were being asked in these first few are find the domain of each rational function, find its vertical, its horizontal asymptotes, if any, on the corresponding graph. Now we're going to go right after the VA, right out of the gate, and we're going to go looking at the bottom, which is x plus 3, and we're going to set it equal to 0 and get x is equal to -3. Now this is a vertical asymptote, okay, and this will have a direct relationship on the domain. Now I'm going to write this domain in two different ways, and it'll be really up to your teachers on how they really want to focus on it. We could say that all real numbers are working on this particular deal, with the exception of x not equaling -3, because there's a vertical asymptote at that location. You could also write this in set notation, which would be -infinity, goes all the way up to -3. It doesn't include -3, but then it's union with -3 on to infinity. Now notice that the brackets are soft in this particular case, and they're soft because they're saying that they're not including -3 once you get there. This would be the other notation, so I'll put the word or here. Now, in terms of a horizontal asymptote, now I've got to look at the three different cases that are possible there, and the top does not have any kind of degree to it, so I almost have to think of this as like x to the 0 that's going on there, so that looks like a 1. There's a 0. The top is definitely losing to the bottom, so we're sitting in an n is less than m situation, so y would be equal to 0 would be the horizontal asymptote. Okay? Now, with these two particular values, you really can start to get an idea of what the crosshairs of the graph would basically look like. You'd have a vertical asymptote coming down here through -3, and then you'd have a horizontal asymptote that's going right here that's at that y is equal to 0 concept. And you really already started to coordinate off the graph to decide how the actual shape is going to look. All right, so a very good step and getting us started. Now let's try some more. Vertical asymptote is going to be x is equal to -4, stating that this will end up determining the domain. I'm going to put a D here so that it makes more sense. And the domain would be from -infinity to -4 unioned with -4 to infinity. And I just like set notation because it makes a little bit more sense just trying to connect all the individual dots in terms of the domain. Horizontal asymptote, in this particular case, power of 1, power of 1. We're sitting in an n is equal to m scenario, so y would be a over b, and that would be 2 over 1, which would be just 2. All right, now, the good way to get good at these guys is to practice. You need to practice and practice and practice until you've got it under control. Now, there can be some strange things that you can run into, like, say, for instance, a vertical asymptote is set equal here to, I'm just going to say 2x squared plus 1 set equal to 0. And I hope that some of us can see ahead on this, that we'd end up dealing with x squared is equal to -1/2 and try to take the square root, and we were like, ooh, it's making an imaginary particular situations. Imaginary vertical asymptotes, they don't exist. So ultimately, there are no VAs in this. Now, that can absolutely happen. You can get a vertical asymptote that's not a real number, and it just ends up not having any vertical asymptotes. Okay? Horizontal asymptotes, in this case, if I was talking about domain here, it would be all real numbers, not imaginary ones, but so there's no exceptions in this case. Horizontal asymptote would be, again, comparing the powers, power of 1, power of 2. We're talking about n is less than m, so y would equal 0 in that case. That makes a relatively funny looking graph. If you get a chance to put that in your calculator, which I think I'm going to take the opportunity to do here right now so that you get the idea of thinking about putting things in your calculator too as well. I'm going to give you some cautious little details here. First off, if we're going to put any kind of graphs into our calculator, specifically denominators are dangerous. You want to make sure that you put parentheses to denote that the denominator is a full entire entity, because your calculator will not know that unless you tell it so. So 2x squared plus 1. And we'll probably see a situation here where there's no vertical asymptotes. We get a very strange looking graph out of this. and no real line that's separating one half of this graph from the other. Okay, pretty cool looking, huh? All right, let's keep trying. Number 4. Number 4, vertical asymptote can be a 5x plus 2 is equal to 0. It can absolutely be a fraction, negative 2/5. That's not unheard of. Again, the domain in this case would be from negative infinity to negative 2/5, soft bracketed unioned with negative 2/5 to infinity. You end up with a couple of vertical asymptotes. It just makes this domain restriction relatively longer. A horizontal asymptote, in this particular case, there's a tie in power, so the horizontal asymptote would be y equals negative 3/5. And you're off to the races. Number 5, another situation where we're dealing with no vertical asymptotes, so the VA is none, because we can definitely tell that's going to make imaginaries. But on the other hand, the horizontal asymptote, the first time we've actually seen this, the power upstairs is larger than the power downstairs, so n is greater than m, and we would have none in the category of horizontal asymptotes. This makes a very strange looking graph. I believe it's the hill. Check it out on your calculator and see if you can come up with a graph. Number 6. Now here's where we might end up generating something that is strange, or like question mark here. Once things have been completely factored out, you might see that the x definitely got canceled as a repeating factor from numerator to denominator. That x being canceled is x equals 0, and this one generates a hole in the graph, not a vertical asymptote. Now the leftover returner down there in the denominator would generate a vertical asymptote, so this graph will have both a vertical asymptote and a hole. It'll look like on the graph it only has one vertical asymptote, but if you were to chart this in your table, you would notice that there is another discontinuity at 0. Now, taking a look at some, those are VAs. Now, HAs are tenuous. You want to look at the original when you make the determination of a horizontal asymptote. So going back to the original, I'm just going to kind of erase my little pattern right here. This would be an x, this would be an x squared, and ultimately, since that would take place, the top would be smaller than the bottom, n would be less than m, and we would deal with y equals 0. Okay? Now, as I said, if I was going to graph this particular graph, I would definitely want to denote the whole thing as being separate. And you can't go wrong by putting in parentheses where parentheses belong. I'm going to actually show the entire thing here, x minus 4. You open the barn door twice, you close it. And this particular graph, as you'll see, will have a vertical asymptote at 4, and you won't see the one that's happening at 0. Now, that one that's happening at 0 is really happening in this table, and you can see it right there happening at 0. That's where the hole is at. And if they were correctly going to draw this, we would put the vertical asymptote here at 4 as it comes across and goes down, and this one comes down around like this. There should be a hole generated right there on the graph, and it won't show it on your calculator, but you would need to show it on your own individual graphs. Okay, pushing down by Calculadora. Let's push down and try these last couple of problems that are on 2.6. And last but not least, what if we came across a question that had not been completely factored? Now, we can take out a GCF in this particular case and get a cancellation. So we would generate a hole at x equaling -2, and we'd also generate a vertical asymptote from the leftover ones, which are going to be 0. Now, this starts to make us think about domain, too, which we haven't gotten a chance to get back to. That'd be -infinity, well, that's a -infinity, up to -2, unioned with -2 to 0, unioned with 0 to infinity. And that would be a set notation, or you could write the exceptions where x is not equal to those two values. The horizontal asymptote in this case would be about power notation. We're talking about n is still less than m and y would equal 0. So watch out for those kind of things and make sure you're paying attention to the generalized rules. You should have learned all these in Algebra 2 honors. Now, if it isn't already factored, like this one was before, you should try and factor the ones after. That's x would factor here, factors of 4 that make -5 are -4 and -1. Those would add to -5. Neither of those are going to cancel, and this one would generate 2 vertical asymptotes. One would take place at 4, and another one would take place at 1. Both of those places, and you end up generating multiple sections where the graph can take place. Horizontal asymptote, again, going back to the original, top is winning, the bottom is losing, so n is less than m, or y is equal to 0. Now, the reason we go through all of those individual ones during this particular case is because we want you to understand those fundamental pieces before you ever put pencil to graph paper. So make sure that you've got that understood.